we get started. I do want to mention that Dr. Roth is still looking for volunteers for math counts on Saturday. It's really easy work, especially if you need service hours for anything. It's a middle school math competition. If you're not familiar with math counts, they do some test taking things earlier in the morning, and then they do like what they call a countdown round, like a head-to-head thing near lunchtime. The grading really is just right or wrong. They have to write their answers on answer blank, and you just count it right or wrong. You count how many they got right. That's all the grading is. It's super easy. For your trouble, not only if you need service hours, if you need those, but you also there's some donuts and stuff provided in the morning and lunch for lunchtime. So if you're interested in helping out Dr. Roth, just contact him. He'll give you the details. It's not super early in the morning either. I think the first grading starts at like 9:30, so it's not super early on Saturday morning. But anyway, I know he'd appreciate the help if you got the time. So just contact him if you're able to do that. So anyway, let's continue on our discussion that we started last time, right at the end of class, which has to do with probability mass functions. I wrote down two of the conditions that we have for probability mass function. The first is that we want to make sure that our function is always non-negative no matter what we plug in for the little x. And then when you add up all of the possibilities for the function over the entire sample space, you get 1. I wrote this for x in the sample space, and plugging that into the function. Remember, there's that switch over using that random variable function. Depending on what our experiment is, our sample space may not be quantified necessarily, right? For example, if your experiment is flipping a coin, your outcomes are heads or tails. That's not a quantity, right? However, you might quantify that with saying you assign 0s to heads and 1 for tails and see what happens. That makes sense? So that's what the random variable part does, is it switches your sample space, whatever it happens to be, into real numbers. It quantifies it, or it gives numbers to it. And then our probability mass function assigns probabilities based on what the input is in the sample space. So for example, in the example I just said a second ago, if you assign 0 for heads and 1 for tails, then you would have f of x is equal to a half. If you plug in 0 or 1, then it would be 0 otherwise, because there are no other outcomes of that experiment besides getting heads or tails. And then you can start doing some analysis of what would be the expected value out of that, and so on, so we'll talk about as we go forward. However, a lot of times we'll equate what we mean by the sample space as being the same thing as we've already quantified or given numbers to each particular outcome in the sample space. So when I write it like this, I really do mean that this S here has quantities or inputs that make sense to plug in here. So everything we do going forward, we'll be looking at probabilities of things where there are numbers of things. So for example, maybe you roll a die 10 times, and you want to know how many times you rolled a 4, and maybe you're counting how many times you rolled a 4. So in that case, our outcome there would be a quantity that you're plugging into the probability mass function. In any event, well, then hopefully that'll make more sense as we go along. The last condition that I did not give you for the probability mass function talks about that it really is about probabilities. So the third condition is that if A is a subset of the sample space, then the probability that you're in A is just the sum over all x in A of the probability mass function. So your probability mass function here is assigning probabilities to events. There's just that intermediate step that you're quantifying. Okay. So last time, the example we were doing talked about wanting to figure out what the constant was to multiply by this function to make sure that we actually had a probability mass function. So basically, we're going to use this last condition here, not this last condition, this condition that I have written here to help us figure out what the C is. We talked about doing that in a finite case last time, where we had the numbers from 1 to 10, and we used that little sum formula. You should be able to do something similar for part E. I mentioned that last time, right? Not too bad to figure that one out. So let's do the C and the F there, because those are discrete sample spaces. If we think about our X as being the values of the sample space, those are discrete sample spaces, but they're infinite, which we haven't quite talked about yet. So let's look at part C there. So we've got our C, we've got our purported probability mass function is some constant times 1/4 to the X power. And the values that you can plug in for the X are 1, 2, 3, and so on. And what I said, I don't really mean. I said those are values you can plug in for the X. Actually, you can plug in whatever you want for the X. It's just that if it's not one of those things that's listed, then we assume the probability mass function is 0 on those things. So the set of X values where the probability mass function is actually honest to goodness positive is what we refer to as the support of the probability mass function. And we'll talk more about support when we get to continuous distributions. But the support just means it's the values of X that I plug into my function and I actually get honest to goodness positive values. If I try to plug anything else in, I get 0. Then we just basically ignore it. If it's 0, then we have no probability there. All right. So again, we're going to use that condition that if I add up my probability mass function over the entire support, I have to get 1. So I know that if I do the sum from X equals 1 to infinity of that function, of the function, I have to get 1. Notice I have an infinite series here. So if I want to make sure that these are honest to goodness probability mass functions and make sure that I get a sum that makes sense, we need to worry about the convergence of the sum. Talk about that in calculus. Pardon me. Good news is that there won't be a lot of different infinite series that we need to know. We need to play around with geometric will be the most important one. We'll actually have something that's called a geometric distribution later on in this chapter. So the geometric will be the most important one we do. We will do a partial fractions example as well. You'll see that's going to be in part F there on that sheet. Partial fractions go up from time to time. Partial fractions also pop up in differential equations when you're doing the Laplace transform, for example. So that's another reason why I want to do that particular example, because partial fractions does pop up from time to time, and I want to remind you about how to do partial fractions. Okay, but most important infinite series that we will do in this class is geometric. Okay, all right. So remind ourselves about how we do a sum of a geometric series. Let me do this off to the side. I like my geometric series to start at 0 because then the formula is easy. If I start my geometric series at 0 and then my exponent just is n each time, that sums to 1 over 1 minus r. Bless you again. Any more? No? Okay. Of course, what has to be true about your R for this to work? What has to be true about R? Yeah, the absolute value of it has to be less than 1, right? Could be negative as long as the absolute value is less than 1. Of course, again, we're talking about probabilities. You're not going to see any geometric series where you've got a common ratio there that's going to be negative. All of our common ratios will be positive. We're associating these things with probabilities happening. Okay. So for our purposes, yes, we can just say the R has to be less than 1, but just remember, generally speaking, its absolute value of R has to be less than 1. Notice what we have here. We're starting our series at 1 rather than 0. So to make this start at 0, I'm also going to pop the C out in front. We know that we can take the constant out in front. If I'm going to subtract 1 from the X here in my index, what better I do here? Better add 1, right, to make sure everything balances out. That's re-indexing the series. I can make my series start wherever I would like just by bumping the appropriate number back in the inside of the series. So notice when I put in 1 for X, I want this to start with a 1. So if I'm putting in 0 for X, I still want this to start with a 1. So I add the 1 back. I want to make, and the reason why I'm doing this is because, again, I like using this formula because it's easy, right? Okay. So I need my series to start at 0, but I also need my exponent just to have an X rather than an X plus 1. Notice my X is playing a role with N, right? How can I rewrite this to handle that case? What do I need to do on the inside there to rewrite it so I just see something to the X power? Good. Yeah, use your property of exponents that says I can just split that into 2 pieces. And then, like before, that's a constant, so I can just pull that 1/4 out as well. And now I have my geometric series written in a form where I can apply my formula. My R value is less than 1. My exponent is just simply the same as what I'm indexing over. And my index starts at 0. So that I can replace with 1/1 minus 1/4. If I distribute the 4 through the denominator here, I see 3. Right? You just take the 4 and multiply it through, make it 4 minus 1. So I get C over 3 is 1. So my C better be 3 in this case. This will not be the only time we see geometric series. Is this example okay? Geometric series look familiar? The reason why I spent a little bit more time on it is because, again, it will pop up from time to time. All right. Let's do F. I remember what F is. Starts at 0, and it's x plus 1 over x plus 2. Same idea. We still need to make sure that when we add this up over the entire support, we get 1. For our purposes, again, this infinite series needs to converge if we're going to really have an honest-to-goodness PMF. When we start doing expected values later on today, we're going to see that sometimes this series may not converge for certain expected values, but when we're doing the PMFs, they have to converge because it has to add to 1. So these series have to converge. This particular one, you would expect that it would converge. If you remember stuff from Calc 2, if I multiply out the denominator, I get an x squared part. So that should remind you of a special type of series called a P series, where your P is bigger than 1, and those all converge if it's bigger than 1, right? So we would anticipate that this does converge, which is helpful for us. But what we need to know is in order to find that C, I got to figure out the value that it actually does converge to, right? In order to do that, we need to do our partial fractions and actually analyze the sequence of partial sums. Probably did one like that back in Calc 2 or 3, whenever you learned it. Depends on when you learned it. All right, so remember what partial fractions looks like. Oops. The idea is that you've started with a fraction you've already combined, and you want to break it apart into pieces that you would have needed to get that common denominator, right? You're starting with the left-hand side. You're used to start. Try that again. You're used to starting with the right-hand side, finding a common denominator, and getting something that looks like the left-hand side. Partial fractions is reversing that process, right? You knew that this was your common denominator. In order to get this as a common denominator, you need an x plus 1 in one of your fractions and an x plus 2 in the other fraction. Right? Also remember that we won't ever come across this, but this happened in Calc. You need to make sure you have what's referred to as a proper rational function here, meaning the degree of the top is less than the degree of the bottom. If it wasn't, then you had to do long division first to get it proper. If this is proper, then each of these factors are proper. And since we have linear factors, that means they have constants on top. Good news is we're not going to do a lot of partial fractions things. I'm just trying to remind you of those things from calculus. In case you pop up again. We won't do anything horribly complicated. The even better news is that if you really had something that you wanted to do a partial fraction decomposition with that was more complicated, computer algebra systems will do that. Find a computer algebra system. If you've got one for your calculator, great. If you find one online, they'll all do partial fractions. All right. Next step here, clear your fractions. When you multiply both sides by x plus 1 times x plus 2, the x plus 1's cancel in the first fraction, the x plus 2's cancel in the second. Now, you could, and it's certainly valid, you could set up a system of equations and solve for the a and b that way. Because you can equate x coefficients on both sides, and you can equate constants on both sides. But that's not the easy way to do it. The easy way to do it is to recognize this needs to be an identity. This needs to work no matter what you plug in for x. So there are two really good numbers to plug in for x to get the values. What do you think those two really good numbers are? -1 and -2, because they make those factors cancel out, right? If I plug in -1, the b goes away. If I plug in -2, the a goes away, right? Now, not that it's important in this particular problem, but sometimes students forget to put it in for the x that's on the left-hand side, too, if there's an x. Make sure you plug it in everywhere. If I put it -2, we get 1 equals -b, so your b is -1. And if you put in -1, you get 1 equals a. Pretty straightforward. So now, going back up to the original problem, we can pull out, going back up to the original problem, back up here at the top, we can pull out the c, and now on the inside, we have 1 over x plus 1 minus 1 over x plus 2. Oops, so it should equal 1. All right. Now, in calculus class, let me scroll over just a little bit more. In calculus class, you probably would write out, you should write out, what the first term is in your sequence of partial sums, what the second term is, what the third term is, what the fourth term is, and so on down the line, and take a limit. Because remember, the actual definition of a series converging to a number is that number is the limit of the sequence of partial sums. That's the technical definition of a series converging, right? Create the sequence of partial sums and take its limit. Okay? We're going to be lazy. Okay? So here we're going to just start writing out some terms and see what happens. Okay? What's the very first term in this series? What do you get? And leave them at, don't simplify it, just leave it as you get the individual fractions. What do you get for the first term? It'd be 1 minus a half, right? That's what you get when you put in 0. Put in 0 here and put 0 here. I get 1 minus a half. What's the next term? A half minus a third. The next one is a third minus a fourth. And keeps going, right? What's happening if you start looking at things? Yeah. This is where you have to be a little bit careful, which is why in calculus you're very, very careful about actually creating a sequence of partial sums and taking a limit, because I'm going to do infinite, what looks like infinite cancellation, which you cannot do, by the way. Doesn't work. But those all end up going away, right? For every finite sum, you'll get cancellation until that last term. But that last term is getting smaller and smaller. So your sequence of partial sums will get closer and closer to 1, because everything else is going to go away. And so we just get C has to be 1 in this case. Like I said, we're going to be a little bit lazy. The reason why we're going to be a little bit lazy is because if you're asked the problem, it has to converge. Okay? You have to be a little bit careful about infinite cancellation, because this kind of looks like the following. That series where you've got a 1 plus a negative 1 plus a 1 plus a negative 1 and so on down the line. How do I know where to cancel? Do I cancel these two and get 0, and then cancel those two and then get 0, and then cancel those two and get 0? Or do I leave that alone, cancel those two and get 0, cancel those two and get 0, and so on down the line? Is it 0 or is it 1? Can't be two different numbers, right? Okay. The difference between this and here is because notice our individual terms are in parentheses, right? It tells us how to do this. If we had these, if this was your first term, and this was your second term, and this was your third term, and so on down the line, that would go to 0. But the way I wrote it originally, I didn't tell you what the grouping was, so you couldn't do that, right? This is telling you what the grouping is, so you can do a little bit of more work with that one. I'm only telling you this because you have to be careful when you try to do infinite cancellation. It may or may not work, depending on the scenario. Okay. Good news is that we're not going to have to worry about anything weird yet. Weirdness comes later. All right. It's okay? Partial fractions look familiar? Are you all sufficiently bored about it now? Okay, good. I'd rather you be bored and remember than me just gloss over it and you not remember. Okay, all right. All right, let's look at the next one. Mainly because I want to talk about what would they mean by a bar graph in the book. So they've got a probability mass function here. Our support is 1, 2, 3, 4, 5. And then your PMF is 1 plus absolute value of x minus 3 all over 11. One of the reasons why they want you to start doing these as bar graphs or histograms is because we're going to switch over to continuous distributions later. And in some applications, we're going to want to approximate discrete distributions with continuous ones. And so they want you to, if you think about these bar graphs, you might be interested in what the shape looks like later to know what kind of a thing you might want to approximate with. We'll get into that later. We're not worried about that today. Today I'm just worried about, can you create the bar graph? All right, the easiest way to do this, you just compute the probabilities. What do you get when you put in 1? 3/11ths. When you put in 2, 2/11ths. You put in 3, 1/11th, and I think it goes back up again to 2/11ths and 3/11ths. It's just literally plugging in the x's, right? And simplifying. Not too bad, I hope. What does this need to add up to? If I added them all together, what would it need to add up to? 1, right? We've plugged in every single possibility in our support. So if I add up all those probabilities, I better get 1, which you can check quickly. If they tell you something is a PMF, you should assume that it really is going to equal 1 when you add them up. But it's always a nice check to make sure you did the arithmetic correctly, especially if you've got a small example like this. All right. Here's what we mean by bar graph. I'm going to make my scale on the bottom be 1, 2, 3, 4, 5. I'll make my scale be 1, but I label 1, 2, 3, 4, 5 because those are the numbers that we plugged into our PMF. I made my scale on my y-axis 1/11th because they're all both 11/11th. And then you just literally make a single line segment that goes up to the height that corresponds to the probability. That's what a bar graph is. You may have heard bar graph in another context where you draw a bar, right, a rectangle. In this textbook, bar graph literally just means draw a line segment up to where the height would be for the probability. So for 1, we draw 1 up to 3/11ths. For 2, we would draw up to 2/11ths. For 3, up to 1/11th, 2/11ths, 3/11ths. That's bar graph. That okay? There's also the idea of probability histogram. Probability histogram. Histogram means that basically if you've done bar graphs before, you usually think about rectangles. Bar graphs with rectangles are usually for qualitative data, meaning there's no connection between the things that you're counting. Histograms are for quantitative data, meaning that you've got connections between the numbers from one to the next. For probability, we always draw histograms. That means your rectangles would butt up next to each other. So when you draw a histogram, you would make a rectangle that straddles each of your numbers. You could draw a different graph. I'm just drawing on the same graph. So your histogram here would have the same heights. Each of these rectangles will have the same heights as your bar. We'll just thicken it up to bars, to rectangles rather than just a single line. So yes, Declan. Usually we split it halfway around the data point. So in this case, it would go from a half to 3 halves, 3 halves to 5 halves. We want the data. We want these all to have the same width, whatever they happen to be. So I want to straddle each of these, and I wouldn't want that to go all the way over the y-axis. The reason why we want these to have the same width is later on, again, we're going to talk about continuous distributions. And if you remember your stuff from calc, when you started adding up things underneath your curve, you first divided it into rectangles, and your rectangles typically had equal width, right? And then you just make them get smaller and smaller. That's exactly what we're going to do later. So it's going to turn these infinite sums into integrals. This is how we'll handle it later. Is this okay? Yes. The red ones are the probability histogram. So the red one's the probability histogram. Okay. Pardon me. All right. So let's do a couple more examples here. These are some specific examples of the types of distributions that we're going to come up with later on in this section and analyze them. So we've got 3 defective items out of 50. You're going to take a sample of 10 without replacement. You're going to count them, and then the random variable here counts the number of defective items in the sample. So first, what's our support? What are your values that you can have for the x where you'll get a non-zero probability? What are your possible numbers for x? X is counting number of defective items. So what are your possibilities for x? 0 to, how many total defective items are there? 3, so 0 to 3? Okay. All right, those are your only possibilities, right? You could take 10 items, not get any defectives. You can take 10 items, get exactly 1 defective, exactly 2, exactly 3, right? So we want, first, let's see if we can come up with the PMF. We should be able to write it down. Your PMF should be giving you a probability. So I'm going to make a fraction to start with. Let's figure out the denominator first. You're taking 10 items from a group of 50. What's your denominator going to be? And it's without replacement. What's your denominator going to be? So your denominator is going to be the total number of selections that you can do. You're taking 10 out of a group of 50. What's your denominator going to be? 50 chose 10. Good. Yep, exactly. It should be 50 choose 10. Good. That should be the denominator, right? The denominator has absolutely nothing to do with defectives or non-defectives, right? Total number of items you have is 50. You're selecting 10 of them. It's without replacement. And I couldn't care less about the order, right? That's why it's a combination. All right. We want X defectives and the rest non-defective, right? How many ways can you choose defective items? Choose the X defective items out of 3. So it depends on the X, right? But how many ways can you choose X defective items from a group of 3? There's 3 choose X, right? Does that fill up the entire sample? No. The rest have to be filled up with non-defectives. How many non-defective items do you have left? 47. How many non-defectives are you going to pick? If you pick X defectives, you'll choose how many non-defectives? 10 minus X. Good. So there's your PMF. We did a problem like this before, didn't we? This type of distribution pops up, like I said, later in the semester in this section. What word do I want? Chapter. This is called a hypergeometric distribution. I think I even used that word before when we did this example. Okay. All right. So again, we want to choose X defectives. The rest have to be non-defective. There was a total of 10, so those two numbers have to add up to 10. These two numbers have to add up to the total number of things that you are choosing from, right? You have 3 defectives to choose from. The rest are not defective. Those have to add up to your total. These two have to add up to the number you're choosing. Notice that It obviously makes, well, at least I hope it's obvious. It obviously makes no sense to have x be negative because you can't pick a negative number of items, right? Even though this could go all the way up to 10 and you'd be okay to be not negative, there's only 3 defectives possible, right? That's why we have to stop at 3. Okay. So there's our PMF. Now that we have a PMF, we should be able to answer the questions. The first one says, you want exactly 1 defective item. What do you need to plug in for x to get exactly 1 defective item? 1, yeah. So for part A, you would do f of 1. Whatever that simplifies to. Don't care what it simplifies to. That's perfectly fine. That's what calculators are for. Okay. All right. What would be different about part B then? Good. You want f of 0 plus f of 1, right? So this one's asking you for the probability that the random variable is less than or equal to 1, right? At most 1. The things that satisfy this inequality are x equal to 0 and x equal to 1. We said that we can calculate the probability of an event as add up the probability mass function over every single number that's in the event. So in this case, it's 0 and 1 are in the event. This is going to be f of 0, f of 0 plus f of 1. So the first one will be 3 choose 0, which is 1. 47 choose 10 over 50 choose 10. And then the other one number is the same number we got in part A. Again, you could simplify it. It's not horrible to simplify these things because so many things cancel out, but that's what calculators for, which is why I don't care. Even if you're taking an actuarial exam, if you're ever interested in that in the future, they require you to only be able to use a scientific calculator, but even the scientific calculators have combinations on there, so you would still just type it into your calculator. You would have to do it by hand, unless you're really wanted to. Okay? All right, notice again, like I said, we're going to talk about this later as far as a type of distribution goes. But notice the setup. We have a large collection broken up into exactly 2 sub-collections, right? Okay? We're choosing a group from the large connection, and we're counting number of things of 1 type, right? Okay. Also important in this type of distribution is that, but without replacement. Okay. That's what makes it hypergeometric. As we're going through and collecting more specific types of distributions, we want to make sure that we can identify why they are the way they are, why we're using a particular distribution. This one, as soon as you see large collection divided into 2 groups, you should think hypergeometric. Make sure that really is, but as soon as you see large collection broken into 2 things, and you're selecting a group of them, it's probably hypergeometric. Yes. It's 3 different things. Okay. Large collection. This is telling us I have 2 groups, defective and not defective. And I'm taking a sample without replacement. So there's really 3 pieces that I'm looking at. Like I said, we'll focus more on that later about how we identify it, but I just want to make sure we're starting to think about it now. This one should look very similar to that. Now, again, this problem is asking us for a specific probability. What I want to do is see if we can set up the probability mass function first. Okay. We've got 100 light bulbs, and we're picking 5 bad ones. Okay. They're going to select 10, and we want the probability of finding at least 1. Okay. We're going to inspect 10 bulbs. Are they going to? Is the inspector going to select the exact same bulb 10 times? No, it's going to be 10 different bulbs, right? So selecting a group of 10, right? And again, we've got the large group broken into 2 pieces. Defective light bulb, not defective light bulb. Okay, so this is why we do hypergeometric. Okay. What are your possibilities for number of defectives that you can select? What are your possible x values? Yeah, 0 to 5, right? So possible x's. Zero to 5. So your PMF then, again, denominator here will be what? Good. 100 things to choose from. We're choosing 10. And on top, we'll pick some bad bulbs and some not bad bulbs, right? How many ways can you choose X bad bulbs from a group of 5? 5 choose X. If there's 5 bad bulbs, how many not bad bulbs are there? 95. If you've chosen X bad bulbs, how many good bulbs do you select? 5 minus X? Or 10 minus X, sorry. Good. I don't know where I got 5. I don't know where I got 5 from, but 10 minus X. Good. Again, top numbers here have to match the total. Bottom numbers here have to match how many you're choosing. It's okay? All right. So this one says finding at least 1 defective bulb. One, yes. I hard to hear you over the ear. Sorry. What did you say? Yes, means the same as thank you, Austin. Yeah, the word bad means the same as defective in this case. Yeah. Yep. And it doesn't really matter what the word is. You just need to be broken into 2 pieces. Is the idea. Okay. We want at least 1. Oh, that's much better. Thank you, Austin. Felt like I was yelling for a while. Great. We want at least 1. So in our context, that would mean 1 or 2 or 3 or 4 or 5, which we could brute force and do. But what's easier? Even it says in the hint. What's easier to do? Yeah, 1 minus none, right? So we can do, writing it as probabilities, I want the probability that x is greater than or equal to 1. In the discrete case, this will be 1 minus the probability that x is, technically it would be less than or equal to 0, but can we get less than 0 here? No. So this would actually be the 1 minus the probability that x is in fact equal to 0, or 1 minus f of 0. So we'd have 1 minus 5 choose 0 as 1. So I could just write this as 95 choose 10 over 100 choose 10. Trace, did you get a decimal?
Yeah.
Yeah, what'd you get?
0.58.
0.58, okay. That's okay. Now notice, of course, we already established that we did this type of distribution, this hypergeometric distribution, because we said the inspector is not going to select the same bulb over and over and over again, right? Well, let's say the inspector had the chance of selecting the same bulb over and over and over and over again. Could we compute another probability in that same way? I'm not going to write down the PMF. I'm going to write down just the possibility. What would happen if he was drawing a bulb with replacement versus without replacement? What would be the probability of drawing no defective bulbs when he did it 10 times? So it'd be 95 over 100 on the first one. Plus or times, right? So it'll be 95 over 100 to the 10th, right? Because we multiply them all together. Okay. So then at least one defective would be 1 minus that. And if somebody put that in their calculator for me. One minus 0.95 to the 10th. Probably easier to type it in that way. 0.40. Okay. So a little bit less likely. But that would be what it would be if it was with replacement. Let's hope it'd be a little bit closer. That's okay. Anyway, but what if this number went from 100 to say 10,000 instead? What if you did 10,000 and only 5 defectives? So in the first case, it would have been 9,995 choose 10 over 10,000 choose 10, right? And in the other one, it would be 1 minus 0.9995 to the 10th. Your calculator do that one? Just curious if it'll even do it with the 10,000 in there. If not, we can do it.
The second one is 0.004.
0049.
Second one.
It might balk at you with the 10,000 if you're doing the combinations. Yeah, there you go. About the same, right? Okay. Notice when your number of defectives, or the number of one of your, you remember we said we take a big group and divide it into 2 smaller groups? If the number of your one of your groups is really, really small relative to the size of the whole group, then these numbers are going to turn out to be really, really close. And that's a little bit easier to calculate than that one is, right? So we can actually approximate this hypergeometric case with this case that we just did if our numbers are big enough. The other type of distribution is the other type of distribution that we'll talk about, which is called the binomial distribution. And we'll talk about that later. But anyway, I just wanted to illustrate that as your numbers get bigger, you can really just do with replacement as opposed to without, and you don't have to worry about doing the extra formulas. This works when you're doing polling, for example, because you're going to take a smaller group of individuals that you're polling against a large population, right? If you ever do a survey, like you're going to do presidential approval or congressional approval or who you're going to vote for, the number of people that you're going to pick from is small relative to the population at large, so you might as well assume that everybody has an equal chance of getting picked. Where that's not quite true, right? Because as soon as you pick somebody, you're not going to pick them again. You're really picking them without replacement. But the change is so small, you might as well just assume that you did it with replacement. That's not going to affect anything in a real sense. That's why I wanted to mention that here. This actually has practical applications when you're doing statistics. Maybe you don't care, and that's okay too. I will tell you that people do care. It just may not be you, and that's okay. All right. A professor gave students 6 essay questions and she'll select 3. A student has time to study for only 3 questions. What's the probability that at least one's selected, all 3 are selected, or exactly 2 are selected? This looks similar, doesn't it? So again, the student is going to pick 3 to study, and they need to figure out if it's the 3 this professor chose or not, right? So again, you're going to have, what are going to be your, if you think about X being, or X representing, this is something that we'll concentrate later on as well. We're going to let X count the number of questions the student studied that are on the exam. This is another concept that we're going to concentrate on as we go forward, and I know I'm taking a lot of time harping on things today. You're probably sick of listening to Seth's voice. Put too fine of a point on it. No. Later on, we're going to have connections. A couple of big connections in particular between 2 distributions, one of which will be discrete and one of which will be continuous. Discrete distributions count things, right? Usually it's answering a how many happened, right? Continuous things are on a continuum. Maybe it's a waiting time, right? Those kind of things. So you have to be a little bit careful. Am I using a discrete or a continuous? This is why I'm emphasizing here that we're trying to count things, right? In this case, we're trying to count the number of questions the student actually managed to study for the ones that were on the exam. It's a counting thing. It's a discrete thing, right? Now, again, if we're thinking about doing this as random selection, is the teacher going to put the same question on the exam just 3 times? No, it's going to be 3 different questions, right? So it's going to be without replacement. And again, we have divided into 2 groups. Student studied the question, student didn't study the question, right? So what are your possible values for X? 0 to 3, good. Our PMF here, denominator will be 6, choose 3. Professor had 6 questions, going to choose 3 of them. What's the numerator going to look like? 3 choose 3 minus X. Yep, agreed. For part B, what would you plug in for X? 3. For part C, you plug in 2. For part A, how would you attack it? Yeah, 1 minus none. 1 minus the probability X is 0. Good. So this was just like the previous ones, right? Are we okay with setting this up? Let's see. All right. So for these probability mass functions or these probability distributions, one of the things that we're going to be interested in is what would you like to see happen on average in the long run? So, for example, if you're rolling a die over and over and over and over again and averaged all the results, what would you expect to see on an average? If your numbers are 1 to 6 and they're all equally likely, you expect on average to be 3.5, right? That's the idea behind expectation. So let's talk about how we do expectation. It's a pretty straightforward idea, actually. And it doesn't. We're going to do expected value of x. That's going to be our what we'll refer to as the mean here in a minute. But in general, if for some reason your book uses the letter u for the function, if u, pardon me, is any function, doesn't matter what the function is, if u of x is any function, then the expected value of that function is, you take the sum over everything in your sample space and you multiply the function by f of x. So you get u of x, f of x is our expected value. You do this in lots of different applications. For instance, if you know that 10% of your grade is based on homework, 20% of your grade is based on each of 3 tests, 20% of your grade is dependent on each of 3 tests, and your finals were 30, you would take 0.1 times your homework average plus 0.2 times your exam 1 score, 0.2 times your exam 2 score, 0.3 times your exam 3 score, and 0.3 times the final exam score, right? To get your final average. It's a weighted average, right? That's exactly what we're doing here. It's a weighted average. Each of these probabilities has this weight assigned to it. Okay? That's what expectation is. If we're just doing expected value of x, when your function is just the identity function, if u of x equals x, then e of x is called the expected value. Or the mean of x, the average. All right. So all this is doing in this particular problem is asking us to do this expected value idea. So for part B up there, we already figured out the C values for these things, didn't we? Okay. So let's do part B. Part B says, if we want to do the expected value of x, we will add up from 1 to 10. The C value is, let's write it this way. We'll do x, that's the function. That's this function u of x, right? We'll do x times the C value that we found last time was 155th. And then we have an x there, right? Now let's start using properties of sums here. I can pull the 1 over 55 out in front. For heaven's sake, stop moving everywhere. So we'll want to add up 1/55 times the sum from x equals 1 to 10 of x squared. You could brute force that, or there's a formula for that. you add up the sum of the first n squares. So 1 squared plus 2 squared plus 3 squared up to n squared. You can use this formula. So in this case, we would have 10 times 11 times 21 all over 6. Whatever that turns out to be. Yes. Say that again. This x? That x is coming from this is this. That's where that one came from. Oh, what does that end up being? 5 times. Was that 7? Yeah. Good. Which, remember, this is kind of a weighted average idea, right? The weighted average idea. Your x values go from 1 to 10, but the x values nearer to 10 are more likely than the ones nearer to 1, right? Because the probability is directly proportional to the x value. So on average, if this was happening over and over and over again, you would expect to see more numbers bigger than 7 than less than 7. So on average, you would see 7. Right? It's skewed a little bit to the top. Yeah, well, it's weighted a little more to the top. Let's do part C, because this has us do another formula. Part C, the C value we came up, or yeah, it was C, right? The C value we came up with was a third, right? Or I think it was 3. Thank you. Yep. So our f of x was 3 times 1/4 to the x, where your x's went from 1 to infinity. Okay. So again, when we do expected value, we'll do x times the PDF or PMF. If I say PDF, that stands for probability density function, which is the word we use for continuous, and my brain switches sometimes to the other word. So right now, if you hear me say PDF, I mean the same thing as the PMF. Okay. And I apologize in advance. All right. I need to know what this adds up to. Well, this requires a calculus idea. Probably this on the board. If I have f of x equals x to the n, what's this derivative? Good. Notice that the power comes down and we decrease the power by 1 here, right? So notice that, pardon me, over here, I know it's weird because we've got x's versus n's, but my x here is not playing the role of x over there. My x here is playing the role of n. This looks like I brought the n down in front over here, right? Okay. So one of the things that we remember from calculus, from your series stuff, we just talked about this a little bit ago. I know the letters are going to be mismatched a little bit because of the way you thought about it in Calc 2 or 3. We just did this a minute ago. We had the power series representation for different functions. This is literally the geometric series formula, just with x for r, right? If you differentiate both sides, notice the right-hand side becomes the series 1 to infinity of x in x to the n minus 1 when I differentiate every single term, right? Bring the power down, decrease the power by 1. Notice it started at 0, but if I put 0 in there, that's a constant. So when we differentiate the constant, it goes away. So we can start the series at 1 instead of 0. Right? look familiar? If you've done power series, it should look familiar. I know it's probably been a minute, but slept since then, I'm sure. At least I hope. Okay. All right. But if I differentiate the right-hand side, I should also differentiate the left-hand side. That left-hand side is 1 minus x raised to the negative 1 power. If I differentiate that, you'll get 1 over 1 minus x squared. 1 minus x to the negative 2. So this is 1 over 1 minus x squared. Right? Okay. Now notice, again, notice over here, my index is n. Over here, my index is x. So my x is playing the role of n here, right? That's okay. But what does this need to be instead of an x in order to be able to use this formula we just talked about? It needs to be x minus 1, right? To make it an x minus 1, we need to pull out a 1/4. And to make it a minus 1, right? I got to pull one of the copies off to make it negative 1 for my exponent, right? This is, I pulled out a 1/4 to the first power, so if I put it back through again, it would add my exponent. So now we can use the formula. The 1/4 is what this is now playing the role of what this x is. So we'd have 1 over 1 minus 1/4 squared. One minus 1/4 is 3/4. So I'd have a 3/4 that cancel, and then we can invert multiply, you should get 4/3. We're going to use this formula again later on. I've already told you this is an example of what's referred to as a geometric distribution. One of the things that we will collect is what expected value is of these different types of distributions. So we'll come back to this again when we do that. Does this formula look familiar, though, at least from Calc 2 or 3, depending on what you did? Okay. All right. I'm not going to do the other ones. This is the idea, though. All right. So let's see what else we got here. This one, we would just brute force. This one asks us to calculate expected value of x and expected value of x squared. Again, expected value of x is our mean, what we would expect to happen on average if we ran the experiment again and again and again and again and again and again and again. That's what the expected value means. Expected value of x squared will help us calculate what we refer to as variance, and we'll talk about that next time, what variance is. This one, though, will allow us to do some properties of expectation, and this is what we'll finish up today. So anyway, let's do the first two. They're pretty straightforward. Again, expected value of x. We're going to do this from -1 to 1, because we only have 3 values to plug in. And again, it's x times what the PMF is. So put in -1 for x, we'll get -1 times. Absolute value of -1 is 1. So I'll just write it as 1 plus 1 squared over 9. The next one will be 0 times 0 plus 1 squared over 9. The last one will be 1 times 1 plus 1 squared over 9. I didn't put it at the absolute value bars because I just wanted to have it going all over the place. Although this one's pretty easy to figure out what it is without even doing any simplifying. What's the answer? It's 0, right? These two are opposites of each other. That is 0, right? So we'll get 0 when we're done. If you think about it in terms of the bar graph idea that we mentioned before, rather than, I'm not going to put an x-axis or a y-axis on here. You've got, this one would be a 4/9. When you put a -1, you'd have a 1/9 here, and you'd have a 4/9 here. right? You'd expect these to happen, the negative 1 and 1, to if you did this over and over and over and over and over again, you'd expect as many negative 1s as 1s to pop up. When you add them together, you get 0, right? So if you average it up, you should get 0. It's not a huge surprise. Notice that when we drew this bar graph, it's symmetric about 0. And it's not an accident that the expected value then turned out to be 0. What's going to be different if you do expected value of x squared? What's the only thing that's going to be different? Those numbers that are out in front will get squared, right? It's literally the only difference. Okay? This will still be the same sum. This will still be the same PMF. This will be x squared instead. You just square those x's instead. What do we get? 4 8/9 when we're done? Okay. Now, that last one looks a little bit more complicated. It should. But let's see if we can use develop a couple of properties of expectation to help us out. First off, what if you do expected value of a constant? Well, by definition, I would take that constant and multiply it by the function, right? Agreed? Well, what can I do with that k relative to the sum? We've done it a few times today. What can I do with that k? Take it out. Good. Now we are adding up the PMF over this. Over the entire sample space. What does that add up to? 1. Right? It's the PMF, so if I add up the PMF over the entire sample space, I get 1. Right? So expected value of a constant is a constant. What if I do an expected value of the sum of two functions? So let's say I call them u and v. What can I do with the f of x relative to the sum on the inside? Distribute. And now I have a sum of a sum. So I can basically just split it up into two pieces. Oops. And notice that the first one is just the expected value of u of x, and the second one is the expected value of v of x. So expected values break up over sums, right? If I put a constant on one of these, I could have pulled the constant out in front as well, right? So going back up to what the problem asked us to do in that last part, and I know I'm out of time, if I do this expected value of 3x squared minus 2x plus 4, the first thing you can do is break it up over the sum. And difference. I can break it up over the sum and the difference. That's what we just proved a second ago. We can also pull out any of these constants. And I could do the last one. I'll just leave it as the expected value of 4. Do we know what those values are for the expected values now? We did those, right? This is 3 times 8/9. This is 2 times 0, and the expected value of a constant is the constant. 24 and 36 is 60 over 9, looks like. When the property that we are using is called linearity. Expectation is linear. That just means that you can break it up over sums and differences, and you can pull constants out. Okay. It does not break up over products. Okay. Breaks up over sums just fine. It does not break up over products. Okay. We'll do more examples of these next time, and do a couple of other special expectation things out of 2.3. So there should be a video about special expected values, special expectations, something along those lines. Go ahead and watch that for Thursday. Otherwise, we will see you. If I don't see you before then, I'll see you on Thursday.